Welcome to Process Injection, breaking all macOS security layers with a single vulnerability. If you have started Xcode since updating to version 14, you may have seen this new function in the template. Application supports secure restorable state, which by default returns true. Now in this talk, I'm going to talk about the vulnerability that necessitated this change and what this actually means, and how this vulnerability could be applied in different ways. I'm Thijs. I'm here together with my colleague Daan. We are the security research team at Computest. We are the research department that we call ourselves Sector 7. Computest is a security company in the Netherlands doing stuff like pen testing, incident response, SOC. But we don't work for customers, we just do research to help make the world better and to talk about it and to publish about it at places like this. Other work that you may have seen from us over the past couple of years is zero-click RC and Zoom at Prone2Own last year, and winning Prone2Own Miami this year with 5 vulnerabilities in ICS systems. But macOS has always been a bit of a background research project for me. If I'm stuck with the main focus of my research and I want to do something else for a change, then what I just end up doing is, well, looking at what's running on my system. So looking at some processes, looking at some files. And most of the time that doesn't turn out to be anything there. But sometimes I do find stuff. So yeah, over the years I've found a couple of things, reported those to Apple. And today I'm going to talk about one of the most interesting vulnerabilities I found. To describe it, I'm going to go quickly over the macOS security model. It's probably well known to most of you here, but I just want to make sure that the context is clear. And then describe this process injection vulnerability I found. And then in the third part, I will apply it for sandbox escape, privilege escalation, and then finally bypassing SIP. So the security model in macOS, current macOS Monterey. First, I want to compare it to like the old sort of Unix, Linux security model. And that's basically means that the users are privileged boundaries, but processes are not. You can see this if you look at files. Files always have an owner and a group, and a number of flags that determine who is allowed to read or write or execute that file. The same thing for processes. If a process wants to attach to another process as a debugger and then read its memory or affect its execution, then they need to be running as the same user. And the exception, of course, is root. Root can always read all files. They can attach to any process, read all memory. So basically, root has access to all of the data on the system, whether on disk, whether in RAM, anything. And this was the security model of macOS up until the introduction of system integrity protection. So this was introduced in 2015 with El Capitan. This is a screenshot from the WWDC presentation where this was announced. And the basic motivation at that time was like 2 things. So adding a privilege boundary between the root user and the kernel, and protecting the system itself from being modified by other software. So the operating system itself should not be modified by malicious software, even if it has root privileges. So you see that there's now no longer just root can do anything, but in order for root to do certain stuff, that it needs to also have something else. And that's what entitlements are for. So if an application wants to load a kernel extension, then it needs to have a specific entitlement. If it wants to modify system files, then it needs to have another entitlement. If you want to debug processes, then there also need to be entitlements probably on both processes. And this is so that those privileges that can then be given back to certain processes, because you still need to be able to update your system. You still need to be able to load a kernel extension. And after the introduction of SIP originally, there have been more and more restrictions added over the years. So debugging any application now requires privileges, and probably need to turn off SIP if you want to attach to some other process. And one interesting feature is, I'll refer to as data vaults. I'm not completely sure if that's the official name for it. but this basically means that there are certain locations on the file system that even root cannot read from without an entitlement. So for example, your mail folder, Apple considers your email to be very sensitive. So if you try to list that in your terminal, then you will get a permission denied error, even if you do it with sudo. And there's also no TCC prompt for this. This is just, it's always blocked, unless you have full disk access. And then, of course, your mail application does need to be able to access those files. So there's a specific entitlement for mail to be able to access those files, and only applications with an entitlement like this can then access those locations. Now, this is a pretty big shift in the security model of macOS. And I don't think many people have realized how much that model has changed things. This also means that there's now different classes of vulnerabilities that are suddenly become very important, like a process injection vulnerability. So process injection basically means that one process is executing code as if it is another process. So it may be launching that process and then adding some shared library, like Wojciech was showing yesterday, maybe replacing certain parts of the application. There's various ways that you might be able to do that. Now, Apple has blocked a lot of these things already with zip. So from the original presentation, there was already stuff like blocking task for PID and stuff like that, and dynamic linker environment variables. And also third-party applications can also prevent a lot of those features in applications if they enable it. So like the environment variables and library validation, which means that you can no longer load a dynamic library unless it is signed by either Apple or by the same developer. But macOS is pretty old, pretty large. It's been written for a long time under the other security model. So there's still a lot of places where process injection vulnerabilities may exist. Now, it's pretty common to find a process injection vulnerability in a third-party application, especially by third-party developers don't often know about these different kinds of permissions. So you often have to explain the entire security model and then why what they are doing is an issue. And then often it's an issue like you can modify the application and then abuse its TCC permissions, so you don't need to ask for webcam permission and stuff like that. And often it's also possible to just downgrade an application, even if it's currently secure, you can downgrade to an older version that may not have the hardened runtime, and then you can inject into that application and grab the webcam or something like that. But those are often just single instances of a vulnerability. Of course, what's way more fun for me as an attacker is a process injection vulnerability everywhere. So that's what this talk is going to be about. So this CVE was a process injection vulnerability in AppKit. So basically it affected all macOS user interface applications. So anything that's following the normal macOS UI. And the feature where this vulnerability was in what's called the saved state, or internally I think it's called persistent UI. And one of the ways you can see it as a user is if you shut down your Mac, you get this prompt with the checkbox for reopen Windows when logging back in. So this is part of that saved state feature, but it's used for a lot of other features as well. So for example, there's AppNap, which is basically a feature where the system can see, well, you haven't switched to this application in a while, it's not playing any music, I don't think you're using it. And what it then says is it asks the application to save its state, it terminates the process, but it keeps just drawing a bitmap picture of the application. So the user still thinks that application is running, but then when they switch back, the application is quickly reopened again and it restores its state. So yeah, the system can save some memory while the user still thinks the application is open. And it's also one of the other things it can do is it can restore your unsaved documents if you reboot while you have a document open. Even if you didn't save it anywhere on your disk, it can still be there if it's implemented correctly. Now, a large part of this already works if you just create a new application. You don't need to opt in as a developer. It already does a lot of this for you, but you can extend it if you need to. So for example, if you have a document-based application, then you may have your own states for the documents, and then you might want to store that state in the saved state as well for each document. Now, those saved states are stored in this directory, in your saved application state directory in your library folder. There's basically two files here that are important for this. There's a couple more. I don't really know what they do. There's the windows.plist file. This is basically an array of all of the windows of the application and a couple of other things like a dock menu, but every window has one entry here. And there's the very originally named data.data file. And this is a custom format, and it's not used anywhere else as far as I know. And it contains a list of records, and each record has an ID that refers to one of the entries in the windows.plist file. And in the windows.plist file, there's an encryption key, and every record in the data.data file is encrypted with AES-CBC, and it's an encrypted serialized object. Now, I don't know why this is encrypted, because the encryption key is right next to it. There are no different permissions. There's no entitlement here for accessing those files. My best guess is that they wanted to store this in the keychain, but that turned out to be complicated or something like that. Maybe the keychain is locked and then your state is gone. Or maybe to prevent these files from being indexed. I don't know. Because there's no integrity check as well, any application can modify it as long as they can just grab the key and modify the state. But what this really is about is this serialized object. Now, insecure deserialization is a type of vulnerability that's very well known in many programming languages, but mainly C# and Java are well known for this being able to lead to code execution. So there's these projects that you can just use to generate your C# serialized object, and that will then run some shell script for you if it's deserialized. Same for Java. I think for Python it's pretty trivial to do as well. I think Ruby as well. And Apple also has a serialization format called NS-coding. But Apple also realized this risk of insecure deserialization. And they realized this back in 2012. So they added a secure variant, the NS secure coding. And that's back in Mountain Lion. But the older version of the protocol is still in use. It still exists. And it's still used in certain places. So to compare those two different variants, so the insecure version, what this does is it first decodes an object, and then it checks, is this of the class that I expect here? And this is a risk, because at the time you check its type, the object already exists. It may already have done stuff. Maybe its constructor is doing stuff, or its destructor is doing stuff. But the secure version, for that to decode an object, you need to specify in advance that it needs to be of a specific class. If it's not of that class, it's not created. So this is much safer because you now can no longer just create arbitrary objects. It really needs to be that class or a subclass of it. Doesn't mean it's impossible to attack this. There still have been attacks against these secure coders, but it's much harder than an insecure version. So I had this idea for an attack. I create a saved state with a malicious serialized object. I write it to the saved state directory of another application. I launch the other application. It deserializes that object, and I have code execution in that other app. This sounded really easy, but then I started looking into this. Well, did somebody else already find such a serialization chain of objects that I can use here? So there's this YSO serial project, YSO serial for C# as well. that you can use for Java serialization or for C# serialization, but nothing like that for Objective-C seemed to exist. I looked into a couple of Project Zero write-ups about secure deserialization, but those all used very specific vulnerabilities in the secure serialization that had since been fixed. So those weren't really techniques that I could apply anymore. So I could not find any prior work on this. It might exist, but eventually I just concluded I had to do all of this from scratch. So finding a chain of objects that I can pass through that into that format to eventually evaluate AppleScript within another process. So how did I do that? Well, I disassembled a lot of those init-with-coder methods. Those are the methods that are used for creating a deserialized object. And what I noticed is that, especially in AppKit, many of them do not support secure coding. Kind of surprised me, but also many of them aren't really objects that you want to send to somebody else. So they're not used for XPC or something like that. So also really no need for secure coding. And also many of those were not very interesting. So they just recursively decode some instance variables and then they're done. So it took a while to find any of them that had anything actually useful. Then the first step I found was the NS rule editor. And when this object is deserialized, what it will do is it will create a binding to another object using a key path also from the archive. So bindings, if you're not familiar with macOS development, they're basically like a reactive programming technique where you can just directly connect a model to a view without having a controller full of boilerplate code in between. So for example, you can have your model as a person, and then you create a view with a text field, and you can bind that view to the name of the person. And then the key path that you have is the name property of that person. And then if you modify the text field, then the model is automatically updated, or if the model is updated, then the view is also automatically updated. Now how this works internally is that if you create a binding, then you should select a property of the object. There's really no check for that. So what you can just do is you can call any method as long as it has no arguments on an object. And whenever you make that binding, it needs to create an initial value so that method is invoked immediately as you deserialize this object. So for example, if you have a NSProcess class, which has a launch method, it has no arguments, so you can create a binding to the launch method, and then at the moment that binding is created, that method is invoked. So you're not supposed to do this. It's not a property that you should be binding to, but by doing this, I was able to call arbitrary methods during deserialization, as long as they have no arguments. And then as a second step, I use this NS custom image wrap. And when this object is deserialized, it decodes two things from the archive. A draw method, which is a selector. It's like a function pointer for a Objective-C method. And an object, but it wouldn't use those yet at this point. But it has a draw function. And when you call this draw function, it will perform the selector that it decoded from the archive on the object that it also decoded from the archive. Passing itself as the first argument. So by combining this with the previous one, by creating a binding to that draw method, I was then able to call arbitrary methods. Although I did not have any control over the arguments yet, I could call these arbitrary methods on objects that I deserialized. Now, sadly, for the next step, I have to skip a little bit because it involves a vulnerability that's not yet fixed. Hopefully it will be in Ventura. So I'm going to skip ahead a little bit and summarize a bit the steps that I just did. So first of all, I could call zero arguments methods on these serialized objects. And I could call any method on these serialized objects. I could use this redacted vulnerability to create arbitrary objects, so not just deserializable objects, but any objects. And then I used actually a similar trick to call zero argument methods on those objects, call arbitrary methods with another redacted part. And at that point, I can basically execute AppleScript. So this AppleScript is running inside another process, so it's running with the entitlements and the permissions of another process. So for example, if I would attack mail, I could just tell it to copy the entire mail database from the data vault to a location where I can read it and then upload it, do stuff with it. AppleScript also means I can spawn a shell, reverse shell, stuff like that. So at this point, I had pretty well compromised the application. But then it turned out that this was not quite enough for everything that I wanted to do. The second one of the exploits that I will show later, this was not enough for. I wanted to be able to execute something equivalent to native code, and it was not yet possible with this. And then what I had to deal with is the hardened runtime. That was really the main issue here. So at this point, I could interact with the Objective-C runtime. I could call methods. I could create arbitrary objects. But stuff that I could not do is call C functions. I could not create any structs. I could not create C strings, no pointer dereference, nothing like that. But due to the hardened runtime, I was not allowed to create JIT memory pages or inside memory at all. So I can not just create some memory, write my payload into there and do jump to it. So memory corruption, that would be possible with the methods that I had, but it would be pretty tricky. And library validation also means that I was not able to load a malicious library into the process, but I could load libraries signed by Apple. Now that's very interesting, because Apple includes quite a few scripting languages within macOS. So I looked at all of those scripting languages, see which of those has a foreign function interface that interacts with C. And I noticed all of these were included in macOS at the time. So Python has been removed since then, in 12.4 or 3, I think, but this all affected Big Sur, so it was still there. So I evaluated all of these things and what I could do with them. For AppleScript, I just concluded it was not powerful enough, didn't give me the primitives to do what I wanted to do. JavaScript had no FFI that I could use. You had to expose the new stuff to the JavaScript world, and I could not access that. Perl and Ruby were interesting, but the FFI modules are not included. So if I wanted to install those, they would create new binaries which would not be signed by Apple, and I would not be able to load them. TCL might work, but I think I'm too young to know what this is. But Python was interesting for me, because Python on macOS did include the C-types module. So I didn't need to compile anything. I could just load the C-types module. With C-types, you can do a lot that you can also do in C. You can call C functions, dereference pointers, C strings, structs, anything. And most of it works with the hardened runtime on. There's a few things. So C-types has a feature where you can pass a Python function as a function pointer, so a C function pointer. And to do that, you need to have JIT memory, so you need to have writable, executable memory. And the hardened runtime wasn't allowing me to do that. But I could just delete all of those parts from the C-types module because I wasn't interested in using them anyway. If I just deleted all of those, I could load the module fine. So in practice, this is equivalent to native code execution within a process. But now I'm still back at the same problem, because Python doesn't have an Objective-C interface. I wanted to load a different language to call C functions, but now I need to call a C function to execute Python. So I was back at the same problem again. But then I noticed that one of the steps that I previously saw was the AppleScript Objective-C bridge. So this is basically AppleScript with access to the Objective-C runtime. It's a framework that's been included in macOS for a couple of years in the AppleScript Objective-C framework. And what you can do is if you load it, and you can then load the scripts from a bundle. So instead of loading the bundle itself, you can just load the scripts from the bundle, and even if that's not signed by Apple, even if there's no code signature on that at all, you can just load it and add new AppleScript into the runtime. Now this was able to interact with the Objective-C runtime, but one interesting thing here is that it can call C functions. So it did give me that extra thing of being able to call a C function, but it cannot create those non-object pointers, structs, C strings, stuff like that. So this gives me just this little step further, but then there was still the issue of how do I execute Python? Because for Python, all of the C functions that I was interested in take a string argument. For example, file path or the actual Python code to evaluate there. And it took me a while to see what I could do there. But if you call PyMain with 0 arguments and null as a second pointer, what it will actually do is it will act like a REPL, just like if you enter Python in your terminal, just the actual REPL stuff would start within the process that I was attacking. So I could create a nil pointer, and I could pass it to this function, and then at that point, I could execute Python on standard input in the process that I was attacking. Now, if you think AppleScript or Objective-C is a little bit verbose, you should see how code in the AppleScript Objective-C bridge looks like. So all of this, you need to prefix stuff with like tell current application or current applications, NS bundles, Alex, and then pass the method name, and it's pretty terrible to read this. But with that PyMain line at the end, I could start as pile REPL within that process. So to go back to that summary of the different steps, I could call any methods on arbitrary Objective-C objects, evaluate AppleScript with the AppleScript Objective-C bridge, evaluate Python, import C types, and then I had code execution basically equivalent to native code. So I could apply this vulnerability on any application, but of course I was very interested in seeing what is the maximum impact I can have with this vulnerability. So if you report something to Apple, you really want to make sure that you have understood the full impact and that you can demonstrate it, because they're not going to figure that out for you. If you want the full bounty, you really need to demonstrate it yourself, is my experience. So first of all, that's sandbox escape. For that, I used what's known as an open panel. It may look quite boring. If you're a macOS user, you probably see this one 10 times a day and you don't think much about it. But it's actually technically quite complicated. So what you have here is that the application may be sandboxed, so the application has no access to your list of files, but the open panel can see your full disk. So the way this works is that the window itself is actually part of your application, but the contents are being drawn by a different service. So you can kind of see this like an iframe on a website, but within an application. And that content, or that open and panel save service is not sandboxed because it needs to see all of your files. Now, as it turned out, for some reason, this open and save panel was loading its saved state from the same directory as the application itself. I'm guessing because you might want to resize the panel and then the state needs to be saved per different application differently or something like that. Not completely clear to me. So what I could do is just write a saved state in my own applications directory, open that panel, and then I had escaped the sandbox. Now this one was actually fixed a little bit earlier by Apple in 11.3 by no longer sharing that directory with the open and save panel service. So I could just use the Apple script evaluation and then execute the shell script and a reverse shell or something like that. At that point, it was outside of the sandbox. Now, privilege escalation to root, and this one required all of that extra Python evaluation stuff. So for this, I used a technique I borrowed from Ilias Morad in unauth-d. So I looked for an application with the entitlement com.apple.private.authorization services containing system.install.apple-software. For example, install command line developer tools. And what this basically means is that this application is allowed to install packages signed by Apple without authorization from the user. So normally if you install a package, the user needs to enter their password or something similar to that. But if you have this entitlement, you can just install any Apple-signed package without authorization. And any installation of a package runs as root. So then, from the write-up of Ilias, there's also this macOS public beta access utility package. This is basically, if you want to enroll into the macOS beta, you need to install this package. And what this package does is that in its post-install script, it runs a command from the disk you install it to. But as a normal user, you can just attach a new disk image or create a RAM disk and then use this service to install to that disk. And at that point, you are running a command that the user specified as root. So just mount the disk, put that file on the same path there, and there's no check if it's a macOS disk. Just go to the installation on that disk, and you're executing code as root. Now, I think Apple has fixed this in the newest version of this package, but because it's still Apple signed, and I'm not sure if they even have a way to revoke package signatures, as long as you have this package, you can just keep doing this attack. Now, if you want to see what that C-types Python code looks like to do this, it's pretty similar to how you would do this from C. You can create an authorization reference, grab that write for the install Apple software, and then pass it to the PK install client that can then use it to install the package. So it's very verbose writing something like that, but yeah, in the end this worked, and I got it to elevate privileges to root. Now finally, I also wanted to bypass SIP, of course. So to do that, I just looked at all of the applications that were available to me. I tried to find them everywhere that I could, and one of the places I looked is on the install disk for the macOS Big Sur beta. And on that disk, I found an application. I'm really not sure what it's supposed to do, but it has the entitlement com.apple.rootless.install.heritable. And what this entitlement basically means is that it can access any SIP protected files. And it's also heritable, which is a nice bonus because then you can just spawn a shell or something like that. You don't need to work within the process itself. And even though this was included on the beta disk image, I could just copy it into a macOS environment, and there the application would still open as normally. So what can you do if you bypass SIP? Well, as I mentioned, you can read the user's email, also the messages database, Safari history, also protected in the same way. I can modify the TCC database, so I can just give myself permission to access the webcam, the microphone, anything like that. I can also persist in locations that are SIP protected normally. So if I write to some SIP protected place, your antivirus would not be able to remove me probably. Maybe with full disk access, I'm not completely sure. Could also probably delete malware removal tool, so Apple would really need to push a software update to delete this. And also, as a final step, I could load a kernel extension without user approval. So there's a database for kernel extensions that the user has approved. And normally the user needs to see a prompt like this where they need to click OK and go to system preferences and also approve a kernel extension specifically. But because I could modify that database, I could just load any kernel extension without the user ever seeing anything happen. So that's not yet kernel code execution because you still need a Apple kernel extension certificate to sign those. But if you would, for example, find a vulnerability in any kernel extension, then you would be able to load that, exploit the vulnerability, and then execute code, or get a certificate from somewhere, maybe. I have a demo of the attack. So first of all, it will demonstrate the sandbox application is actually sandboxed. And then start the attack. The first one should be really quick. The second step takes a little bit longer because it needs to create a disk image, perform the entire installation, stuff like that. It's also not trying to be stealthy in any way, so you can see the RAM disk appearing, but might be some way to hide it from the user. And then the SIP bypass is also really quick because it doesn't need to do anything other than deserialize the object. As you can see, we now have a root shell, and to demonstrate also the SIP bypass, go to the system policy configuration directory. This is where your approved kernel extensions are stored. And I create a new file just to demonstrate that I can write here, which should normally not be possible with just a root user. So a little bit about how Apple fixed this. So to go back to the very first slide, in Monterey, apps can now indicate that they only accept secure serialized objects. So they can just set that secure flag to true. And for all of Apple's apps, this is already automatically enabled. But existing applications may want to store insecure deserialized objects if they have like a document format that they need to serialize there. So for those applications, that method might be needed to return false there. It's not completely clear to me if it's exploitable if the method is not implemented, but the application doesn't store their own objects. I'm not completely sure. I haven't gone through it well enough to say for sure. I reported this to Apple on December 4th in 2020. They fixed the sandbox escape pretty early in 11.3 in April last year. And then the complete fix was included in macOS Monterey, October 25th in last year. And supposedly it's backported to Big Sur and Catalina. Now I didn't know about that. So it was not in the patch notes for Big Sur or Catalina at the time it was released. So as you can see here, it was released on October the 25th. And then they added it to the security advisories page on May the 25th in 2022. I don't check that page very often, so if they update it 7 months later, then I'm not going to see that. So I was assuming they didn't backport it because it's quite an involved change. It's also not in the Big Sur patch notes anywhere, as far as I can tell, so it's a bit weird that they skip a version. I also have not verified if it's correctly fixed or if they use the same approach. Yeah, it's been so long that even getting it to work again to make this demonstration already took some time, so trying all of those old versions, I didn't have the time for that. To conclude, macOS has the security boundary between processes now. It's not just users, and there's all of these different permissions and entitlements that separate processes. And process injection vulnerabilities can break those security boundaries by allowing malware to get extra permissions and abuse them. This was a process injection vulnerability affecting all AppKit applications, and it could be used to escape the sandbox, elevate privileges to root, and bypass SIP. It was fixed in October last year. Now finally, some takeaways. You see that macOS keeps adding more and more defensive security layers, but adding security layers to an established system with such a large history as macOS, that's really difficult. There's all of these places in code that was written like more than 10 years ago at the assumption of a completely different security model and completely different security requirements. And suddenly all of that code is now attack surface. So application can now suddenly attack each other. And there's still a lot of code in the system that is not really making that assumption. And also what I think is an important point to make here is that effort of attackers may not increase if you add more security layers, because sometimes you can just have one vulnerability and bypass all of those layers at once. I have a few references that I used. So the Google Project Zero write-ups for the insecure deserialization, the unauth debug from Ilias, and a few other things about secure coding. And finally, we have a write-up on our website. It's still just the first part of the exploit chain. There's still a part missing. I hope to be able to publish that soon after Ventura is released. Will also be able to find that on our website. Now, do you have any questions?
And can you repeat the question for the live stream, please?
For choosing Python and AppleScript for Objective-C, would you consider all Swift for that step?
So the question is, did I consider Swift for the AppleScript and the Python parts? So I could not compile Swift and then try to load it because the dynamic or the hardened runtime would not allow me to do that. I think there's this Swift playgrounds-like stuff, but I'm not really sure. I haven't looked into it if I would be able to load that and execute Swift like that. I haven't looked into that. It might work. Yep.
So JavaScript for automation has the Objective-C bridge. You can also call C functions, and you can call code from different libraries. It seems to have the same limitations as JavaScript with the players and structs. But the code is, when you're using the Objective-C bridge, is pretty messy, but it doesn't seem quite as messy as the AppleScript Objective-C bridge. So I'm curious why you would choose the AppleScript one over, if there's a particular reason why you choose AppleScript over the JavaScript.
So I think there's a couple of different ways that you can execute JavaScript. So there's these direct methods, and there's also this JavaScript for automation. I'm not completely sure how to call that from Objective-C. So it may be that this was not possible. I'm not completely sure, but I think I did try it and then eventually just gave up because I already had Python working for this.
This affects all versions of macOS, right? Like it goes back
Yeah,
forever,
probably
essentially.
for at least, probably back to the introduction of SIP, probably affect all of those, yes.
Cool. And Apple backported just a few versions, you said?
Only to Catalina and Big Sur, they said, although the release notes don't really make that clear. Okay, thank you.